Hi, welcome back to MEN 221. Today we are going to talk a little bit more about how to draw free body diagrams, more specifically how to deal with constraints. Okay, so that is really what we are looking at. You remember we talked about this idea that in engineering problems, constraints are really important. That is, things that restrict the motion, and we have to figure out how to deal with that kind of a situation. So let's take a look what the heck we mean. So if you look at you can see this dog, this is a nice dog, and it's able to catch this frisbee and all that. And you can see it jumps up and down. You can see it can do all kinds of tricks. So I'm just trying to show you what happens when I want you to pay attention to the frisbee. Okay, so if you look at the frisbee, there are two things that occur. One is the man throws the frisbee, and when the frisbee is in flight, it is not connected to anything. Can you see that? That's the really key thing. In which case, it's actually pretty easy to draw the free body diagram for the frisbee, because I can draw gravity like that, and then maybe there's some drag force. That's it. That's easy because those are the two forces that act on it, and that's the end of it, right? But what happens when the dog catches the frisbee? Now, yes, gravity is acting, but what about these teeth? How do we represent the teeth, the effect of the teeth? We remember we talked about the fact that we are going to represent the external world by forces and torques. The reason to do that is we want to make the body into a free body. Newton's laws can be directly applied only to free bodies, not to constrained or connected bodies. As long as the frisbee is floating around, you can draw the free body diagram and you can apply Newton's laws. The minute it makes contact with the dog's teeth, it's not free anymore. The dog decides what it does. It's constrained. And when that happens, we have to deal with it in a different way. Okay, now let's look at a different example. When in engineering application, you can see this is actually a bottling plant, and I'm going to show you what happens here. You can see the bottles are moving in perfect synchronization. It's actually labeling the bottles, it's actually covering the tops of the bottles, and you can see that it's very tightly controlled motion. Can you see the bottles? They are very tightly controlled motion. Most engineered objects are like this. It's not like this freely floating frisbee. It is completely constrained to move in a very specific way. So we have to be able to figure out what to do with these constraints. Okay, so the way we deal with that is the following. Okay, what we do is we are going to replace the constraints like guardrails, grippers, etc. in the video. You could see there was all kinds of things in the video, right? All kinds of constraints when the bottling plant moved. What we want to know is what to do with the constraints, and the way we deal with that is to treat the constraints by adding unknown forces. So I'm going to add unknown forces, which are called the forces of constraint. The purpose of these forces is to constrain the body, to make it, prevent it from moving. Okay, so contact forces, forces that contact the body, are divided into two kinds. Motive forces, things that cause the body to move. This is what we mean by external forces. For example, when I throw the frisbee, the force of gravity is the motive force because it's causing it to accelerate. Same with the force of with the drag force. Then we have constraint or reaction forces or restraining forces. Their task is different. They prevent relative motion. So these are causing accelerations and these are preventing relative motion. Notice that the word is relative. That is, it is preventing one object from moving with respect to the other. And when you draw the free body diagram, we know the values, magnitude and direction of all these motive forces, but we do not know the magnitudes and directions of these constraint forces. So this we will know, this we won't know. And part of our task as engineers is to figure out how much constraint force is necessary. The reason is because that's what determines whether the body will behave the right way or not. So finding out these constraint forces when we are given these motive forces is one of the critical tasks of doing structural analysis. Okay, so let's look at a very simple idea. We are going to look at a connection. In this particular case, it's just a welded connection. This bar has been welded to the other one. It's a boring connection. Nothing can happen. In fact, it will prevent all relative motions, which means that it cannot translate along the x-axis. Not allowed. Not allowed. No translations along the x, y or z axis are allowed. How do we do that? How do we make sure that translations along x, y, z axis are not allowed? By applying constraining forces. So you notice that constraining forces are required to prevent motion. In one sense, this is opposite to how we think about forces. We think forces are required to cause things to accelerate, right? But constraining forces are required to prevent things from accelerating, to prevent things from moving. So in this particular case, I need Fx to prevent it from moving in the x direction. I need Fy to prevent it from moving in the y direction. I need Fz to prevent it moving in the z direction. I need torque mz to prevent it from rotating around the z axis. I need a torque mx which prevents it from rotating around the x axis, and I will need a torque my to prevent it from rotating around the y axis. Notice all of these things are required for prevention. Okay, so this is a very important idea. So constraint forces or reaction forces or restraining forces are required to prevent motion. Very good. By systematically and carefully removing the weld, that is by removing certain of these things, we can allow certain motions. That's the basic idea. Okay, so let's look and learn how this works. So in 2 dimensions, if you look at a body, you can see it can rotate. I showed this rectangle rotating, and we need to prevent the rolling by applying a torque mz. If I want to prevent it from rotating like what it did, I have to apply a torque mz, that is torque around this direction. So this is required to prevent rotation. Okay, but if you prevent just that, it can do that. See, it's not rotating, right? It's translating. So to prevent that, I have to apply a force Fx. So that's called swaying. When you talk about swaying, that's moving sideways is called swaying, and you need to prevent that. And last, but if you do those two things, it can still move that way. So you need to prevent that by applying a force Fy. And that's called heaving. Going up and down is called heave. Going sideways is called sway. And rolling around like this is called roll. Okay, so I will need something to prevent it from swaying, something to prevent it from heaving, and something to prevent it from rolling. Okay, this is a fully constrained object. If you supply all three, the rigid body will be locked. Basically, you cannot move it with respect to the other objects. Okay, that kind of a joint is of course called a welded joint or a built-in joint or a completely fixed joint. Okay, so there are the three forces. Can you see? This was no swaying, no heaving, no rolling, means I have Fx to prevent sway, Fy to prevent heave, and torque to prevent rolling. If you this is on this body. What about this guy? If you draw the free body diagram on the other side, there. If you draw the free body diagram on the other side, you will get equal and opposite forces. So you can see this one is opposite to that, this one is opposite to that, and this one is opposite to that. So these two bodies share common interface, and then you can apply Newton's third law, which is action-reaction principle. If you ask, okay, you told me that I need Fx, Fy and moment to prevent these things, how much force do I need? How much torque do I need? We don't know yet. We know that if you weld it, you will need these forces. Only after solving the problem by using Newton's laws and calculations and so on can we actually figure out how much force we need. So these will all be unknown forces. Okay, so now we have an idea what is a welded joint. All the other joints in 2 dimensions are obtained by systematically allowing certain motions. So let's look at one example. This is called a pin joint. A pin joint, let's go up here. You will see what a pin joint does. It allows free rotation. Can you see that? It allows free rotation. So in fact, you can see that here there's a pin joint up here, there's a pin joint up here, and you can see it allows free rotation. So you can see that? Excellent. So now let us see what a pin joint looks like. If it did not allow any motion, we would have Fx, Fy torque, right? But I want to allow rotation. So what happens is I will quietly remove the torque. If I am not able to supply the torque, it will be able to rotate. Now my free body diagram will look like this. Oops. Okay. So a big example of a pin joint is shown here. This is actually what is there in a bridge. Can you see this gigantic pin joint here? It will allow this top platform, it will allow it to rotate and adjust itself. By the way, I want to show you that applying these two forces is the same as doing this pin joint. How do I show that? Can you see here? Those are these two forces. So now I'm going to only redo this pin joint by applying these two forces. So here goes. You can see that, see, it allows only rotation. If you apply only these two forces, it will allow only rotation. You see what I mean? If I remove one of these forces, it will do other things, but you got the idea, right? So that's what a pin joint looks like. A pin joint, so a pin equals fixed minus torque. So if you get rid of the torque in a fixed joint, you'll get a pin joint. Okay, very good. Now the next kind of joint we're going to look at is what is called a pin slider. Okay, so let's look at a pin slider. That's a pin slider. So you can see, you can do all kinds of things. It can slide and rotate. So just to show you what this thing will look like here, can you see it can slide and rotate? Can you see that sliding and rotating? Right? So there you go. It slides and it rotates. So you got a guide to slide it and you got a pin to rotate it. Okay. So what does that look like? Let's start. No motion. All three forces are there. Now I want it to slide in the x direction. So I'm going to remove this force. And I want it to rotate. So I remove the other force. When I remove these two things, what I will get is the only force that is there is the y direction force, or the force perpendicular to the thing, because that's the only one that is prevented. So these forces the constraint forces that are left prevent specific motions. Okay, the prevent. So I want you to understand, they are not needed for the motion, they are needed to prevent the motion. This is quite different from the kind of forces that you have seen in physics, which always make things move. Here they are preventing things from moving. That's why they are called constraint forces. Okay, this is the big idea. So once you get that, then it's pretty easy. So a pin slider equals fixed joint minus torque minus tangential force. Okay, so that's the basic idea. A pin slider equals fixed joint minus torque minus tangential force. So it left with only normal force. That's how the thing works. Okay, so just to get you an idea of what a pin joint, what a pin slider will look like, look at your common dragging suitcase, the thing that you use to go anywhere. So what the reason is, because you can see it can move this way and it can rotate that way. Can you see that? So for this suitcase, if I were to draw the force at the corner, it will be only this. That's this guy, and then there will be gravity, right? And there will be somebody who is pulling it. This is the motive force. This is motive, and this is constraint. This causes motion going forward. This will make it go down. This one is preventing this corner from falling through. You can see how that works, right? So the constraint force, motive force. That's how it works. Okay. Now let's look at another example. If you look at wheels, wheels are actually a very tricky thing, but an important idea. In fact, even in that roller, there's a small wheel, right? So if you look at a wheel, if they are not powered, so for example, if you look at a bicycle, the back wheel is powered, right? Front wheel, no power. So at the front wheel, it is like a pin slider. In this particular case, can you see that the front wheel is powered and the back wheel is not powered? So at the back wheel, it will look like a pin slider. Right? It's also called a rocker joint. That is, if you have something that looks like a easy chair, like a rocking chair. You know what I mean? A rocking chair, because it's not powered, it will have only one force that looks exactly like a pin slider. Okay, so remember this, non-drive, non-powered wheels are like a pin slider. These are the rules that you have to remember. Okay, very good. Now we come to a cable connection. This is a very easy thing. I have something and I'm pulling it with a cable, and if you want to see what that will do, here goes. You can see it allows this thing to roll and it allows this thing to swing side by side. Can you see that? So a cable connection allows this thing to go back and forth like this. It allows this thing to swing like this, and it allows this point to move like that. This is another kind of a pin joint, just to make sure you understand. Okay, so this is another kind of a pin joint, and to understand what this does, here is the no motion situation. All forces, all torques are there. Now I want to allow sideways motion, so I'm going to get rid of the torque. Now at this situation, it's able to move sideways, right? But more than that, the force has to be only along the cable. So the final free body diagram, the final portion looks like this. It can swing and rotate, and the force will be there. Okay, so in a cable, cables are special because there is no sideways force. So Fx and Fy are related to each other because the net force has to be along the cable, and this has to be always pulling. It can never push, because it can never push on a string. So these things have to be remembered for cables. So finally, we have all our kinds of joints. So built-in joint, you have moment, you have X force, you have Y force. Value and direction are unknown. Okay, the minute you go here, second joint, torque is 0, but X force and Y force are there. These two prevent this point from moving. The torque being equal to 0 allows this to go back and forth. That's our pin slider, and as well as our wheel joint. Remember, a non-driven wheel. Now, in this particular case, the moment is 0 and the force is along the normal to this thing. The force is like that. The force is along the normal to this thing. Okay. The last one is our cable, and in our cable connection, the force is along the cable. This is the E direction, cable direction, and the force has unknown magnitude but known direction. Unknown magnitude, known direction. Can you see here? It's unknown magnitude and direction, so Fx and Fy are there. Here, unknown magnitude, known direction. In this case, the direction is perpendicular to the slot. In this case, the direction is along the cable. Okay, and you need to memorize these four things. You should know which joint has which kind of force. So the minute you see something like this, you can replace it with that. The minute you see something like this, you can replace it with that. The minute you see something like this, or non-powered wheel, you can replace it with that. The minute you see a cable, you can replace it with that. If you remember these four things, you can do quite a few free body diagrams very easily. Okay, so it's well worth memorizing. So please memorize it. Thank you.